Okay, so right now we're just going to work on worksheet number 6, which is just about H&MRs and its signaling. For this first question, it says label the H&MR with signals that correspond to the hydrogens on the following molecule. So the first thing that I always want to do is I want to label each one of them and their signaling patterns. So I'll start with this one right here. You look at its neighbors and how many hydrogen neighbors they have. So I have a neighbor that's an oxygen, and I have another neighbor that's an oxygen. We know that electronegative atoms usually cut off our signaling, so this one is just a singlet. This one over here is also a singlet. It's cut off by that oxygen, and we're talking about H and MR, so we account for every hydrogen that we see. There's a hydrogen right here, and it's right next to a total of 1, 2, 3, 4, 5, 6 hydrogens. So you do that n plus 1 thing, and you get this one right here, this carbon right there is a septet. And then finally, these two carbons, or these carbon hydrogen bonds, are equivalent. They're exactly the same. So then they'll have the same signal. This carbon right here is next to this carbon. This is its carbon neighbor, and that carbon has a total of 1 hydrogen on it. And so you do that whole thing again, and you get that it's a doublet. This has a doublet. There you go. Okay, now we're going to label everything that's on the H&MR. This one, I would usually try to look like very close into it to figure out what it is, but I can like leave it till last. I can say, I don't know for now, but I know that it's going to be a lot. This one's a singlet for sure. This one's a doublet, and I got a question as to like the height of the peaks. The height doesn't matter right now, so it's just the amount of peaks coming off of this little peak. So you can see that there's 2 things. I'm not gonna go all the way up, but there's 2 things coming from this, so it's a doublet. And then this last one is a singlet. After all of that, we just get to match. So, I mean, you can match however you want. This is our only doublet that we have. The septet is probably the one that we said we didn't know at first. And then you're between 2 singlets, and these singlets are kind of really hard to differentiate between. During my session, I believe we said that this singlet is this, but I looked on ChemDraw because these are really hard to differentiate because you don't know whether the hydrogen that's directly connected to the oxygen is more downfield, which you would think it would be, but there's also that singlet that's in between 2 electronegative atoms. ChemDraw told me that this is the correct labeling for it. But again, you're not going to get something as confusing as this on your test. It'll be like a lot more straightforward. So I wouldn't worry about these last 2 that I just labeled. But it was just practice labeling. Okay, move on to the next one. It's the same procedure. It kind of got clumped. That's where a lot of people got confused. So I just labeled them. You can zoom in. You can see the triplet is kind of obvious. The doublet is obvious. But you kind of don't see that the signal of singlet and doublet are kind of like, they're together. Nonetheless, we know that those signals are going to be the hydrogens on the benzene ring, because if you remember that chart that you were supposed to memorize, there's a range from 6 to 8. And between that range, if you have things in it, it's usually going to be a carbon hydrogen bond, but that carbon is going to be on the benzene ring. So it's referring to all of these hydrogens right here, which again, we can label right now. So then those hydrogens, I'm looking at this carbon, these are its neighbors, and there's no hydrogens on them. So then I would say this is a singlet. Cool. I'm looking at this carbon right here. These are its neighbors, and only one of them has a hydrogen neighbor. So then this is a doublet. I'm looking at this one right here. I look at its neighbors. I have a total of 2 hydrogen neighbors, so I'm a triplet. Looking at this one right here, look at its neighbors. I only have one hydrogen neighbor, so this is a doublet. Cool. And now we can just match them up. I won't really highlight those, but you kind of know that they're matching up to all of these. And again, it kind of gets confusing as to where to put like how downfield each one of them is. All you're gonna have to do is label them on the test, and you don't really have too many similar ones except for the two doublets. But honestly, like they're very close in ppm, and again, they won't give you something as confusing like this on the test. But again, practice. So we have a couple more peaks. We have this one right here, that's a singlet, because it's cut off of any hydrogen neighbors because of that oxygen, that electronegative group. And then we have this last one. These are carbon-hydrogen bonds, so they should show up on the NMR. This is the carbon that we're focused on, and this is its neighbor. This neighbor has no hydrogen bonds, so I would say that this right here is a singlet. I look at the rest of my peaks on my NMR. This is a singlet, this is a singlet. So now we have to use, what's it called? Like downfield, upfield type thing. So we would say, I would label this one right here as more downfield. Oops. And this one right here has this carbon hydrogen bond. There we go. These last ones, they aren't as bad as they seem. I think a lot of you guys had said that you were having trouble or that it seemed really hard when you didn't have answer choices in front of you. But I mean, look at what you're given right here. You're given integration, which is just the amount of hydrogens that are on that specific carbon. And you're given splitting patterns, which is that doublet, singlet, triplet type of thing, plus a formula. So you know whether or not you're wrong based on like how many hydrogens, oxygens, or carbons that you wrote on your predict the compound. Okay. So what I like to do, how I start everything off like all the time, is I do terminal carbons first. Terminal carbons are usually like, I'm gonna draw a random molecule right here. Terminal carbons are the ones at the ends. We know that each of these terminal carbons has like 3 hydrogens on them, right? So something with an empirical formula of 3 is what I usually like to start with, because I know that's the end of my compound. So I'm gonna start with this one. It has an integration of 3, meaning it has 3 hydrogens on it. And I like to start with carbon, but you can always play around with everything. But carbon's usually what it is. Especially if it's 3 hydrogens. And it says that this is a triplet, meaning it has 2 hydrogen neighbors. So I write another carbon and 2 hydrogen neighbors. Now I'm focused on this carbon right here. This carbon has 2 hydrogens on it, so an integration of 2. This pretty much matches with this right here. So this is the carbon that we're talking about. And this is a quartet, meaning it's next to a total of 3 hydrogen neighbors. Luckily, if you look to the right of that carbon that we're talking about, you already have those 3 hydrogen neighbors. So you know you should probably cut it off here. And the reason I'm writing that little cutoff right there is because we know that carbon should have the 4 bonds. Right now it has 3. And so I put that little red mark right here just to say like, at one point we're gonna have to connect it to something else, and only one more thing. Okay, so now the next thing that I look at is how many things I crossed out of my formula. So I'm done with my carbons. I'm almost done with my hydrogens. I only have one more hydrogen left, and I have an oxygen left. Usually when you have an oxygen in your formula, it means you have a carbonyl group, an ether, an ester, or an alcohol group. And alcohols are very popular, so that's probably what we're going to be using here, especially because we have that one hydrogen and it's very downfield, more downfield than everything else. So then what I'm going to do is I'm going to say that's another piece of my puzzle. OH will connect to H. And we know that oxygen likes to have 2 bonds, so then it's already bonded to a hydrogen, and we know it's probably going to be bonded to something else. Now we have our 2 puzzle pieces together. All of our formula is completed, and you can just connect these 2 together. So these 2 are connected, and so you make it look pretty. It's a big eraser. There you go. And that will be my product. Cool, cool, cool. For this test, I don't believe that you're gonna have to be doing any of this. Even then, like, you know you'll have some idea of how to do it. But for the following tests, you're going to be given bonus questions or bonus points, and they're not really bonus like gimme questions. It's going to be you having to solve an NMR and putting it into a roadmap, which we'll talk about later. But just know like this is going to keep coming back, so it's like good to get good at it now. Let's try this last one. Again, I like to start with empirical formulas of 3. So we have a 6 right here. Perfect. 6, you obviously can't have 6 hydrogens on a carbon. So that means we probably have something that's identical. We have an identical environment, chemical environment. So I'm going to write this. These 2 carbons are probably going to be around the same things. So I'm going to do a little connection going to the same place. And again, this is like a very common thing to see. Like you're going to see as you keep practicing that these things just like commonly occur. You'll get this little fork always. Okay. So I wrote those 6 hydrogens there. And then I look at the splitting pattern and it's a triplet, meaning that whatever this is connected to, which is probably going to be a carbon, especially because of the formula, it's going to have 2 hydrogens on it. Perfect. And it looks like we're pretty much done here. You can check this last one, which has an integration of 2, meaning it has 2 hydrogens on it. So we're obviously talking about this right here. And it has a splitting pattern of 1, 2, 3, 4, 5, 6, 7. So it's a septet, which is perfect because we have a total of 1, 2, 3, 4, 5, 6 hydrogen neighbors, meaning that that carbon that we're talking about is a septet. So you just proved it all. Okay, cool. So if you guys have any more questions on any of this, you can email me. Or you can see me in office hours, whatever you like. Hope this helps.